Hello, Pavel.
Hello, do you hear me?
Yeah, we can hear you. And I'm very happy that you're here. And your audience, you all know Pavel? No? Yeah, a few people know Pavel. Pavel has been contributing quite tremendously to our field here in amateur radio and software-defined radio, because he has created an FPGA image and for the Red Pitaya, and this is why probably most of you guys who have been using the Red Pitaya and amateur radio have been using his code. So I'm very glad that we were able to have Pavel here and contribute here live, not in person, but live here to the 11th SDRA. And he's bringing some new research. And yeah, Pavel, your talk has been pre-recorded, and we'll be able to raise questions, and you will answer questions later. And I'll hand over the control to our video team to play the pre-recorded video. Please, video team, go ahead.
Hello, everybody. I'm Pavel. You might know me via my software projects for the Red Pitaya boards, but today I'm going to talk about my recent open source SDR hardware project. Here's an overview of my SDR related projects. I started to play with the Red Pitaya boards around 2014, and I managed to release my first SDR applications for this original Red Pitaya board in 2015. These applications and others could be found at the link shown on the slide. And since then, since 2016, I started to develop more applications for the Red Pitaya boards and the boards from Transelectronic and Digilent. And since last year, I started to be interested in developing SDR hardware projects. And to give you an idea of what kind of projects from the hardware point of view I'm working on, here's an overview of the original Red Pitaya boards and its main components related to SDR applications. So Red Pitaya has two RF inputs connected to two fast ADCs, analog to digital converters. It has also two RF outputs connected to dual channel analog to digital converters. It has a system on chip with programmable logic and processing system, a microprocessor, and it has also an interface to communicate with a computer. In case of the Red Pitaya boards, it's a gigabit Ethernet interface. And also, I would like to mention my applications for the Red Pitaya board. Since I got some feedback from the users of my applications, and I could identify the most popular among them. Apparently, the most popular SDR applications for the Red Pitaya board is the SDR receiver compatible with HP SDR, and this application provides 8 receivers in case of the original board. This original board has a smaller FPGA and currently costs around 470 euros. And for the more advanced model, which is Red Pitaya SDR Lab, what has a bigger FPGA and costs also more, around 780 euros. But thanks to the bigger FPGA, this application provides the 16 receivers. So the most popular applications for this kind of hardware apparently are the multi-channel receivers with as many receivers as I could fit in the available FPGA resources. But what is the motivation for my recent hardware project? So the Red Pitaya boards were very amazing in 2015, around 10 years ago, but they are slightly less so these days because they are a little bit more expensive than in 2015. The hardware is the same as in 2015, and the more advanced SDR Lab board is quite overpriced. In the same time, we had quite some progress in the industry. There are new FPGA and system-on-chip families that appeared. The older FPGA and system-on-chip families are now more affordable than before. And since recently, custom printed circuit boards assembly services have become very accessible. So to illustrate the current price level on boards with a similar chip as on the SDR Lab board by Red Pitaya, here's an example of a board by QMTech that has exactly the same uh, system on chip chip on the board. The only difference is that this board doesn't have the analog to digital converter and digital to analog converter, but the price difference between this board and the Red Pitaya SDR Lab board is a factor 10. So, and we could probably add ADCs to this board via the expansion connectors that are available on this board and obtain an SDR hardware what could be still cheaper than the Red Pitaya SDR Lab board. And so to develop a custom ADC module for such a board, I looked at the services provided by GLC PCB, and I found what GLC PCB can make either entry-level PCBs or very advanced PCBs with up to 32 layers. And in the same time, we can provide components, put them on the PCB boards that they produce and solder it together to provide a fully assembled model that can be sent directly to people who order them. And the quantity of models could be as low as two assembled models per order. So it's possible to order 2 ADC modules for QMTech board, for example, receive them and eventually share one of the models with some other interested people. I also tried to gather some requirements for this kind of hardware. So I get some feedback from radio operators, either who are already using the Red Pitaya boards or who are interested in the applications that I developed for the Red Pitaya boards. So one of the main requirements is to have a low price for such hardware, but in the same time provide 16 receivers as available on the Red Pitaya SDR Lab board. And these receivers should be compatible with popular SDR software like CW Schema Server, OpenWebRx, etc. Basically, radio operators who are interested in receiver-only hardware similar to the Red Pitaya SDR Lab board, but for a lower price. So I prepared the development plan for this project. So the idea is to use the QMTech board that I showed previously as the main board with the FPGA and communication interface. You can see a diagram of the complete system at the bottom of the slide. So on the right is the main board by QMTech with the FPGA and communication interface that would allow to communicate with a computer. Basically, it's 1 gigabit Ethernet. And on the left is the expansion board, what I wanted to develop. It consists of fast ADC, clock generator, power supplies for both ADC and clock generator, and then it should also have input protection, low pass filter, and balancing unit. And to make this expansion board easy to order by people who are interested in, I also plan to write instructions for ordering assembled expansion boards from GLC PCB. So here's my approach to design such an expansion board. So I started by selecting components available from GLC PCB. I noted all the part numbers of these components because they are needed for the assembly service. I also draw all the footprints for all these components and generated net list containing all the components, their interconnections, and their part numbers. And from this step, I used KiCad software to draw a printed circuit board with all the components on it. And once the design was ready, I used GLC PCB fabrication plugin for KiCad to generate all the fabrication documentation required by GLC PCB. Here's how the resulting expansion board with ADC looks like. So it has a connector on the left to connect it to QMTech board. And then it has a fast ADC with LVDS outputs, a clock generator, which is crystal oscillator. Then it has all the linear voltage regulators to power ADC and crystal oscillator. And on the right side, it has RF input protection and 30 megahertz low pass filter. So when I ordered these expansions board, I ordered 2 of them, and here is the current price for this kind of order. So the total for 2 boards is around 180 euros, so making the cost of each of the expansions boards around 90 euros per expansion board. And as you can see, the main part of the cost is the price of the components, and the next one is the assembly service, which costs around 40 euros. And then there are also taxes, what are quite important. So yeah, so but still the result is quite interesting. I would say we have a QMTech board for 90 euros, then ADC board for another 90 euros, making the total price of the assembled system around 180 euros. Once I received my ADC expansion board, I soldered connectors to connect it to the main board and to the antenna. And when I connected them together, added the cooling to keep both the ADC and the system on chip at very reasonable temperatures. And I obtained my system, what allowed me to develop and test my applications for this system. So once I prepared all the applications, I put together a small website that contains the instructions for ordering assembled expansions board from GLC PCB, and also a few applications providing 16 receivers. So to conclude this first project, the performance of this system is similar to the RedPita SDR Lab. The price is a few times lower. It's around 200 euros. All the source code and documentation are available at the link shown on this slide. And already several dozen expansion boards like this have been successfully ordered by radio operators in different countries. So I consider this project quite successful. And based on success of this, my first hardware project for SDR applications, I started to think about the next project. In this next project, the idea is to develop both the main board and expansion board as open source hardware. The diagram at the bottom shows an overview of the main board on the right. So it has an FPGA from the Kintex 7 family, an SFP plus connector for 10 gigabit Ethernet interface, and SODIMM connector for the expansion board. It also should have the power supplies for all the components and to provide the power to the expansion board. And the expansion board this time should have a faster ADC and with more inputs, basically 2 inputs with 250 megahertz sampling rate. The details and discussion of this project can be found on the next-gen SDR mailing list at the link shown on the slide. I already identified all the components for the main board and started to drawing the PCB and started to estimate its price. So the price of 2 main boards with 10 gigabit Ethernet interface and FPGA is around 360 euros for 2 boards. Basically, it makes the cost of each board around 180 euros. So it's more expensive than the QMTech board from the previous project, but I couldn't find anything similar, a board with 10 gigabit Ethernet interface in this price range. So I think it's still interesting to develop this hardware for the projects that require fast interconnect to a computer. So to conclude my presentation, I would like to say what I find GLC PCB assembly service very amazing. It allowed me to produce the expansion board with ADC as my first SDR related hardware project. And I'm now working on the next project with 10 gigabit Ethernet interface. And if you are interested in this project, please join the discussion on the next gen SDR mailing list. So that's it for my presentation. Thank you for your attention.
Okay. Yeah. Thank you very much, Pavel. The 10 gigabit thing caught my special attention because I've been in my job as a computer scientist with data centers. I've been dealing with 10 gigabit connections quite a lot and optical lines and how to connect and build up 10 gigabit networks. So this is probably something new to many of you guys. Who in the audience has a 10 gigabit network at home? Yeah, this is cool. I also. So 10 gigabit is quite a step. There are the direct access, those DAC cables. Depends on where you purchase them. Sometimes you buy them from Cisco for 300 bucks. Sometimes you just use legacy ones, which are kind of 40, 50 euros, something like that. But it gives you a real boost in the network. So 10 gigabit is it's a new thing. It's a new dimension of network processing. So this is really cool. Pavel, I very much appreciate your work because it brings us to also to what I mentioned before, Thomas, the new boundaries, the new speeds of DACs and ADCs. And it will give us a new level of processing. So this is truly the future. Questions from the audience? Markus, what about you?
Yeah, sure. I mean, why not? So on your 10 gigabit device, you had like a Kintex and not a Zynq on there, which means that you will implement a complete like networking stack on the FPGA. It's mostly a solved problem, but that also gives rise to the question of how are you planning to actually, what is the software on the other end of the cable? What will that entail? Will it just take UDP packets and get the samples from there, or will there be something more intense where you could exchange, say, tuning settings like for the digital down converters that you might have on that chip or on an FPGA? How complex are you planning to do that? What's the scope that you're currently envisioning for that digital design?
So thank you for the question about the software. As you say, yeah, the plan is to use UDP protocol to send the samples from the FPGA to the computer. And then the idea is to basically send all the samples without downsampling of the FPGA, since the bandwidth of the 10 gigabit connection allows this kind of transfer. And on the computer, the idea is to use the software what actually currently designed by other software developers to deal with this kind of bandwidth. So at least I don't recall the exact names of the software, but I remember there are at least 2 projects where all these samples are received and then processed locally on the computer with samples rates up to 100 or even more mega samples per second. So the idea is to use these programs and interface them with future hardware. But eventually other possibilities are also open. There is no problem to implement digital down converter on the FPGA and tune it, etc. So I don't see any problem with this, because the FPGA what I'm planning to use is actually bigger than on the Red Pitaya boards what I used previously. So I don't think there is a limitation on the computing power of the FPGA in this project. And eventually, if more power is needed, there is a upgrade path from this smallest Kintex 7 FPGA to a bigger one, or even to the ultra-scale families, what are more recent families of FPGA. But for these projects, I've selected the Kintex 7 part as the cheapest one, just in case if something doesn't work, I don't lose a lot of money on the expensive FPGA, so I prefer to start with the cheaper one.
All right. More questions? Bleeding edge. Okay, Mario.
Hello, Pavel. Thank you, first of all, for all the work that you've done. You should know that's also inspired me. I've used part of your blogs for the first Q100 base station, so just in case you did not know by now, I've moved back to a pure software defined radio setup, but that's another story. The question that I have about your new SDR is, what do you plan on the RF front end? Is it going to be only, let's say, baseband and shortwave, or are you actually planning to have a general coverage RF front end up to like couple gigahertz, what you would get if you looked into, let's say, something like a Bluetooth or similar hardware?
Thank you for this another interesting question. Actually, for the moment, since the system is modular, there is no basically limitations on what could be put on the analog module. But the reason why I'm using this baseband ADC is the result of the feedback from the people on the next gen SDR mailing list, because when I started this project, I put together a small voting poll where people could express their interest in what kind of bandwidth, frequencies, etc., and interfaces with the computer they are interested in. And apparently, most of the voters, there were around 10. Yeah, so it's not the big voting pool, but at least most of the people were interested with this kind of technology, just faster ADC in baseband and preferably dual channel to do things what require two synchronized RF inputs, and also the SFP interface, as it's fast enough and also allows electrical isolation of the radio from the computer. So it's one of the reasons why it's SFP plus and not USB or PCI Express. So yeah, to return back to your question, so for the first version, I plan to use this dual channel ADC with 250 megasamples per second, but there is a possibility that if this first iteration is successful and there is enough interest in different ADCs or some other radio chips, it's possible to implement an analog module using other ADCs for have maybe a mixer to access high frequencies, or an external mixer to, so everything is possible. And that's the idea, to have a project modular and open source, so people could use some of the models, develop their own models, and I think it could improve the speed of development of the new projects. Yeah, hopefully I answered your question.
Okay. We have a number of questions from the chat. We need a microphone.
Yes, we have some questions. The first one is, do you plan to implement timestamping? The bandwidth should be there.
Indeed, it was already requested on the next gen SDR mailing list, and I don't see any problem. At least we could implement as a first step a relative timestamp. So basically put numbers on all the packets of the samples, and eventually for an absolute timestamp we need to synchronize with some precise time reference. It would be more difficult, but at least the first request was let's at least assign numbers to all samples or to all packets to make sure what if samples are lost, we can detect it easily on the software. But the next step eventually could be to add hardware for, I don't know, GPS synchronization or something more precise, and add absolute timestamps. But yeah, there is absolutely no problem to implement it.
Okay, thank you. Next question. How does cost scale with volume? Especially, does assembly cost drop at the same rate as component cost?
Yeah, good question. So far, I'm looking at low volumes, and it's already impressive that actually GLC PCB services allow us to have a very interesting price just for 2 assembled boards. And the basic GLC PCB assembly service has an option for 2 boards or for 5 boards. And indeed, the assembly service cost is the same, I think, for these 2 quantities. So you can order 5 boards, and it will be already the components and maybe taxes what will be the main component of the price. So indeed, the assembly cost drops with the volume. And already going from 2 boards to 5, the price difference quite significant. But I think I don't hope that the project will be as successful as I will have to produce tens of hundreds of boards. My idea is basically to keep it low volume, and it's amazing that GLC PCB allows basically custom production of small quantities, so I don't have to check how to send boards. Basically, GLC PCB receives order, produces board, sends it to the people who want to play with them, and all this infrastructure for me is very amazing. And so basically it's completely distributed production where GLC PCB does everything.
Okay, next question. Would it be possible to design and connect a transmitter board in addition to the dual ADC board?
Yeah, good point. Actually, I don't think there is any limitation. Yeah, for a moment, the transceiver is not my priority because apparently the people who are interested in this kind of projects, they are interested mostly in receivers. But I could imagine a module with a similar chip like on SDR Pluto or some kind of boards where all radio components are integrated. You basically have receiver, transmitter, mixers on the same chip, and it's possible to develop a module with this kind of chip, and it will provide in the same time transmission access to very high frequencies, and still could be used with the FPGA board and SFP plus interface, but basically will provide some kind of SDR Pluto, but with fast interface. So yes, I think it's not impossible, but we should make sure what kind of chips could be used to satisfy these requirements. Yeah.
Okay, one last question. With a sample weight of 250 megahertz, how hard was the design of the board to make sure that all the differential lines were the same length and so on?
This is not yet designed. Yeah, so it will be hard, but I'm still working on the FPGA board. So it will be next part of this project. So ADC board is not yet designed. So the project is in the very beginning, and there is still possibility what the SFP plus interface, which is actually two 10 gigabit pairs, what could fail for some reason, because maybe I made mistakes, maybe GLC PCB can't produce this kind of board well enough. So yeah, for the moment I'm at the stage of the designing FPGA boards where could be surprises, but I will take care of the length of the LVDS pairs for the expansion board, and then yeah, all the length should be matched. But already for KMTech board, even it had a slower ADC board on the expansion board. I just did this exercise to try to match all the VDS pairs to the same length. So I don't see a big difficulty to do the same thing for 25 or 250 mega samples per second. So I'm ready to do it, and I will probably do if the FPGA board works once it's ready.
Okay, last question. Any more questions?
Yeah,
no more?
Okay. I have a question. Pavel,
You have
I'm very glad that you entered our conference now. I think it was 1915 when I invited you to come here. And on 1916, I'm not quite sure, 2016, sorry. I invited you to come here, and you said, well, I'm not sure if I have a focus on SDR in the next year. And therefore, it takes a long time to keep you here, but nice that you come here. My question is, have you any analog measurements done with the new board you presented here? And any
the ADC board for the KMTech, huh?
Yeah.
Actually, yes, I did some. I can't show them right now because I don't have slides with me, but I did a few tests to compare the analog performance of this board with Red PTI SDR Lab, and the performance was quite similar. And there were other people who produced this board for them, and they did the reception tests comparing this board with SDR Lab and other hardware, and the conclusion was that this new board performs quite well, yeah, and similar to SDR Lab by RedPIT.
Okay, thank you very much.
All right. So, Pavel, also from my side, thank you very much for coming in. Thank you for giving this talk, and thank you for presenting your work. And yeah, well, my wish is that maybe we meet in person next year, maybe in 2 years here in Friedrichshafen.
Yeah, why not? Thank you for inviting me and for all the questions from the audience. It was a pleasure to participate. But I think my next year participation would depend on the success of this new project. So if it succeeds, I will be glad to discuss it. But if it fails, maybe not.
Yeah, I'm pretty sure it will be a success already now. So thanks a lot. Please give a warm applause to Pavel. Thanks for joining.